Today, we are going to talk about a problem that plagues chemical treatment programs across the globe. The problem we want to solve? Failing chemical pump power systems. Oftentimes, chemical injection pumps are powered by a solar panel and a battery. This is especially helpful for remote locations that don't have access to grid power. Unfortunately, failing batteries are one of the leading causes of underinjection in chemical treatment programs. In fact, WellAware baseline data captured from thousands of chemical injection systems has shown that 48% of solar-powered pumps have experienced some sort of catastrophic power failure so far this year. Why is this such a problem? Put simply, when batteries go bad, pumps stop injecting, which can put assets at risk of downtime and failure, and can put people in harm's way. The battery failure problem is especially sinister because it can be hard to catch in person. Think about it. A technician usually goes to a remote location to check on a pump during the day, and this usually means the sun is out and shining on the solar panel. In this scenario, the pump often runs on the solar panel alone and is injecting without issue when the technician shows up. But at night, it's a different story. The power system switches over to the battery, and if the battery has failed, the pump will not be able to draw enough power and it will fail to inject chemical. Getting this problem fixed is a high priority for many chemical program managers and operational engineers. The good news is that this is a very easy problem to solve with WellAware On Demand Chemical. Let's jump in to see how. As you can see here, we are looking at the WellAware platform for on-demand chemical, where we can view data, make decisions, and correct problems. And what we're looking at specifically is a dashboard of various performance metrics for the site in this chemical program. And what we see is we've got a problem. The Brady site, highlighted on the first row in the pump uptime and injection variance metrics, is red and performing poorly. So let's click in on the Brady site and see what's going on. As we look at the site dashboard for the Brady site, we see a lot of red and a few things stand out to us. First, we're performing very poorly on pump uptime and injection variance. As we dig deeper, we can actually see that the 24-hour minimum voltage that we've measured on this location is 5.7 volts DC. Now this is a 12-volt pump system with a solar panel, so 5.7 volts represents very poor performance. And we can see that play out in the observed usage rate. We're injecting 2.24 gallons per day, but we're trying to inject 5 gallons per day. So the recommendation here is to replace the battery and/or the solar regulator to get this back on track. Let's take a look at the chart to see how this actually plays out. As we look at the chart screen, we see that the power system is indeed failing. If we zoom in here on the pump power, shown in red, we can see the cycle of charge and discharge at day and night, and we start to see that that system is slowly degrading over time to where we're actually experiencing very poor performance. We can see that being reflected in the difference between the observed injection rate in purple and the injection rate set point in orange. As the power system fails, the observed rate doesn't keep up with the set point and we have underinjection. We can also see this in the product volume curve as we see the rate of decrease slowing down to not deliver the right amount of chemical. So how can we fix this problem? It's relatively simple. What we will do is set up an alarm on low power to help us identify when there's a problem and when it escalates. So let's click on alarms here. So what we're going to do is create some alarm conditions for when the battery starts to fail and when it has failed, so we can see if that condition escalates. So we'll come in here to edit alarm conditions. We're going to add a new alarm condition for the pump asset, the pump voltage measurement, and we'll set this as a low threshold alarm. We'll call this alarm battery failing, and we'll want to get notified anytime the voltage drops below 10.5 volts. We'll set a standard alarm precedence of 50 to keep this as a standard alarm notification. We'll click Save. Now what we want to do is create an alarm condition that'll let us know if this escalates. So obviously a voltage below 10.5 volts is not great, but that could be a transient issue that gets resolved after a period of poor weather with cloud cover where the solar panel isn't able to charge. So let's add another alarm condition that would show us when this escalates. So I'll click Add New, select the pump asset, the pump voltage measurement, and another low threshold alarm, but I'm going to call this alarm battery failed, and I'll set this at 9.5 volts. I'll give this an alarm precedence of 100, which means that if this trips, I'll get an additional notification that the battery has indeed failed. So I'll save that alarm and click close. Sure enough, now that we've gotten some more data from this chemical injection system, we've received this alarm and I've received a text and an email notification. If I expand this incident, I'll see a couple of things. We see that it first triggered and then escalated from a battery failing to a battery failed condition. Now what I can do is I can acknowledge this alarm, which will show that I am taking responsibility to get it fixed. So I'll click acknowledge and I'll click yes. And that way I've acknowledged this and it's been recorded. So now I'm going to go out and fix this problem and we'll see how it corrects itself. All right, so we've gone out, we've replaced the battery, and as we can see, things are doing better. So we had our technician go out. We can see the voltage drop to 0 as we replace the battery. Of course, we were still getting data because the WellAware Connect device does have battery backup to make sure that it continues to report even during a loss of power. We see a note here from the technician that the battery was replaced and the system is okay. And as we can see, yep, it does appear that the voltage has become more stable. And let's take a look at how that plays out in the decrease in volume. So we can see that the chemical rate has increased. And now our observed injection rate has recovered back to the set point. So this is exactly what we want to see. Sure enough, as we look at the dashboard, this is exactly what we want to see. Everything is green and we're looking good. And as we zoom back out to the group level dashboard, we see the same thing. That Brady site has recovered and our dashboard looks much better. So as you can see, it's relatively simple to create an alarm to help notify us to pump power failures when we're using solar injection systems with batteries. This is a great way to solve this problem and eliminate the underinjection associated with it to help get our chemical program back on track.